Very good afternoon to all of you. Can you hear me at the back? Okay, great. So welcome to everyone. I can see some new faces and some people who have attended DV Club before. So welcome back those who attended in the past, and a very warm welcome to those who are attending DV Club for the first time. A bit of background before we start. So DV Club is basically a special interest group that focuses on design and verification on specific topics of interest. The topic that we have today is ensuring my design verification is ISO 26262 compliant. When we are pulling ideas on topics for the presentation today, there are a number of ideas that came in. People wanted to discuss about DV challenges for AI, which is the big buzzword today. There were requests for DV Club around some niche areas, focusing on certain other domains. But we thought, with the automotive ultimately moving towards autonomous driving from the current ADAS state, it is very important to have a session around what are the design verification challenges, especially around functional safety. So vehicles of today are in a complex myriad of hardware and software. There are a bunch of sensors, actuators. There are all the ECUs, extremely complex ECUs. You're also moving towards centralized domain architecture. So it's extremely complex. And the design verification of automotive systems becomes extremely important, especially for systems that need to have a high level of functional safety. So we thought that we'll demystify some of these challenges by inviting some eminent speakers from the industry to kind of throw their light on what are some of the best practices around design verification for systems that need to be ISO 26262 compliant, and what are some of the challenges that they have faced and how they have resolved them in the real world. Let me quickly introduce the speakers for today. I'll go through the agenda as well. Our first speaker for today is Sarvesh from NXP. Welcome, Sarvesh. Sarvesh's topic will be functional safety verification for automotive radar SOCs. The next topic will be presented by Dr. Mike Bartley and Marmik Soni from TESOL. They'll present on refining ISO 26262 practices by adopting Gen AI. After that, we'll have a lunch break, and the final presentation of the day will be by Sundar Rajan from Cadence, who will talk on how to ensure my design verification is ISO 26262 compliant. So each session will last for around half an hour. Sundar's session will last for around an hour. How we typically run this is we give the presenters freedom to present their topics uninterrupted, and at the end of their presentation, if there are any questions, then we can take them. There is online participation as well, so we might have questions from the online audience as well. Okay, good to go. Thank you. Over to you, Sarvesh. I'll just quickly introduce Sarvesh. So Sarvesh is a senior lead verification engineer at NXP. He has been working at NXP since 2012. He's currently working on SOC verification in the radio frequency processing product line with a focus on automotive radar ICs. Sarvesh's primary area of focus has been functional safety for the past 4 years. He's been responsible for functional safety verification both at SOC and subsystem level. He's also a certified functional safety engineer from TÜV. Have also worked on formal verification extensively. It's a pleasure to have you on board, Sarvesh. Welcome.
Good morning, everyone. Hope I'm audible. So as Shyam has introduced, my name is Sarvesh, and I work in NXP Semiconductors for basically in the domain of functional safety for automotive radars. This has been my focus area for the past 4 years, and my work has primarily been at the SOC level, but I'm also responsible for functional safety at the subsystem level. So what we'll do is we'll quickly try to look at the focus areas for functional safety. So primarily I've divided into 4 areas that we kind of focus on from a verification perspective. So one of them is the functional area, or let's say the implementation, the actual implementation. We check whether the stuff that has been designed and architected is working as it is. Yeah, so we were discussing about the 4 different areas. Basically the functional way of working, the fault injection testing, the different kinds of safety mechanisms, and the challenges that we face while complying to the standard. So this is our broad agenda, where I'll be discussing briefly about safety, what is the generic safety flow. Quickly, I'll go over the terminologies, types of safety mechanisms, what are the different safety verification techniques that we use, and lastly, generally not much attention is paid to this topic, which is preparation for confirmation measures. Lastly, we'll discuss about some of the issues that we face during verification. So as is customary, I think, we should start with the definition of safety. So the functional safety is nothing but absence of unreasonable risk due to hazards caused by malfunctioning behavior of electrical and electronic systems. So the intention of functional safety is not to prevent faults, but to put our system in a state where mitigation measures can be taken. Should I go back? So mitigation measures can be taken so that there is no unreasonable risk to the driver ultimately. So we all know what are the trends that are driving functional safety. One of the major reasons is we have all kinds of features. We are moving towards autonomous cars. We are moving towards battery operated vehicles, and that is where the systems like BMS come into picture, which have their own functional safety demands. The modern cars, because of the level of autonomy that is being demanded by the customers, by the market, there has to be a certain sense of situational awareness for the cars, and that is where the radar sensors come into picture. One more important thing is the compliance to the safety standard. It has, let's say, traversed through the supply chain. It is no longer the responsibility of, let's say, one particular player to make sure that the product is compliant to the safety standards. So the OEM, the tier ones, the tier twos, everybody has to play their part. Everybody has their own share of responsibilities as part of this standard. Lastly, what we have to make sure is, on one hand, let's say the technology that is coming up helps us to make sure that we are reducing human error, thereby making the roads more safer. But on the other hand, we have to be sure that the new technology, the new software, the new hardware that is coming up, that is not adding to an extra risk to the already existing problems. So what I mean by that is, the latest example is the Boeing plane crash, right? So they had a software to take care of the angle of attack in the plane, but it overcompensated and it resulted in fatal issues. So, I mean, what I mean by that is the balance of risk has to be on the positive side. So addition of new technology has to make sure that it is definitely safer for technology to, let's say, come into picture when critical decisions are going to be made in the future for let's say, for during the driving. Safety element out of context. So most of the products that at least the semiconductor companies design are designed as safety element out of context. What that means is, when the company is actually designing a product, they do not have let's say, a final customer in mind. What they do is they have a certain sets of assumptions when it comes to, let's say, the specifications that are going to be fed to the chip, the requirements that are going to be coming from one level above. So all those assumptions of use are made, and then the product is designed. What that does is it kind of gives freedom to the, let's say, the semiconductor manufacturer to design a product which can be used in a wide variety of applications. So it will have its own sets of, let's say, assumptions and conditions in which it can be used, but all of that will be kind of published in a document, in a safety manual, so that anybody who wants to use that product surely knows what is the scope of safety, what is the kind of performance that is being guaranteed by the supplier, and that is why this is a pretty standard way of operating. There are instances where companies do make sure that, I mean, if you have a lead customer and it wants you to develop a specific product for them, then obviously the safety element out of context doesn't apply. But in general, yeah, I mean, it is a pretty standard way of designing for most of the safety relevant products. What this slide shows us is a generic safety flow. I have tried to kind of modify it from the point of view of, let's say, looking at it from a point of view of verification engineer. The steps that you see are slightly changed. If you go to the standard, the steps that come before, having safety requirements are pretty elaborate. But since that comes sometimes in the domain of safety architects or sometimes even in tier 1 suppliers, I kind of modified it so that it is easier for us to understand from a verification perspective. So what generally happens at the tier 1 levels is, once you have a set of let's say application in mind, the basic control and data flow diagrams are generated. Based on those control and data flow diagrams, some analysis is done, hazards are identified, and once you have those hazards, what you can do is you can deduce the ASIL rating, and from those ASIL ratings and the different faults that you can envision, some of the safety goals are defined. Once you have the safety goals, then you can actually think about things like safe state, what is going to be my FTTI, what are the different failure modes. Now, once you have the different failure modes, there are a couple of ways of finding out failure modes. Once you have a high-level block diagram, there are safety analysis methods which can be used, like the deductive and inductive methods. We'll talk about them a little later. And from there, you actually, once you have the failure modes, you can devise safety requirements. And this is where actually our role comes into picture, or our role starts as verification engineers. Once we have the safety requirements, we can actually start interacting with the architecture team, reviewing those safety requirements, discussing their relevance at subsystem levels, at system levels, at SOC levels, because it is based on these requirements that architectural decisions are going to be made, and safety mechanisms are going to be in turn added. Once those safety mechanisms are added, that is where our job actually starts. So once we have the safety mechanisms added both at the subsystem level, at the SOC level, we can devise a safety plan. We can devise a verification plan to address those safety mechanisms in a very specific way. Now, what is the verification effort going to entail? So it is going to basically entail 4 or 5 different things. One is, what are the different methods that I'm going to use for my verification of those safety mechanisms? What is going to be my test environment? How am I going to actually connect each of, let's say, my tests to the actual safety requirements? What are my pass-fail criteria? What I mean by that is, how do I decide I have adequately tested the safety mechanism to say with confidence that, yeah, we are good to go? And lastly, the tools. So all these 5 things are, let's say, part of what we, let's say, comply as functional safety verification. A small slide on basic terminologies that we see repeatedly. I'm not going to spend a lot of time here because this itself is, let's say, another half an hour session, but these are some of the terms that we use frequently. So generally, when we see a fault occurring, that fault basically can be at the lowermost hardware element level. When that fault kind of traverses to the upper hierarchy, it can make sure that the element or the function is not able to do its function properly. And once that elevates to another abstraction level, we can say that we have a failure which can result ultimately in a hazardous situation. Now, what we have to do as part of the functional safety verification is, if I have a fault, I have to make sure that I have a safety mechanism in place to kind of detect it within time and make sure that my overall system moves to a safe state. Now, safe state can be defined as a state in which basically there is enough time for, let's say, the driver or, let's say, a system at the higher hierarchy to take preventive actions or take mitigating steps. When it comes to radar products, safe state generally is when let's say if I'm sensing an object and there is an error, what the safe state, what the device will actually tell the outside world is, look, there is an error that I am seeing, there is a fault that has come up. So you might not want to trust the data I am actually sending you. So that is where this kind of metric actually remains important, because this is going to play an important role in further decision making processes. So in functional safety verification, in fact, this is one of the key aspects, the temporal aspects of when the fault is going to be detected and when it is going to transition into safe state. So these are some of the important things that we kind of verify at as part of our verification effort. On the right hand side, you see some of the terms that are used. I'll just quickly go through them. They are generally in the province of safety architect, but as verification engineers, we should be familiar what they entail and what is their actually usage in part of our safety flow. So when I was talking about the generic flow in the last slide, I was talking about basically a couple of methods, namely deductive methods, inductive methods. So the fault tree analysis and failure mode effects analysis are two key such methods which help us to figure out what are the different failures that can happen. FTA is a top-down process. So you start at the topmost hierarchy and then figure out, okay, what are the things that in my design that are going to bring about this result. Whereas FMEA is something which starts right at the leaf level. So you have to, it kind of, it is an effort to figure out if I have a anomalous behavior right at the leaf level, what exactly is that going to entail at my SOC level or at the system level. So these are kind of complementary methods. Both of them can actually help you figure out the different types of safety mechanisms that you need to put in your design. The next one is basically the FMEDA. That is slightly different. It is an extension of FMEA, and the two metrics that are, let's say, relevant from the point of view of safety. Whenever you have a safety assessment, these are the metrics that are looked at to ensure that your SOC is qualifying to the particular standard. So the single point fault metric and latent fault metric, both of them are calculated as part of FMEDA. The probabilistic metric for hardware failure, PMHF, is something which is calculated for every hardware element, and that is based on the historical failure rates that are seen for different elements, and that can be calculated from the FTA as well. So that's a brief introduction about all those terminologies. If you are kind of involved in the safety life cycle of a product, and when you are going to interact a lot with your safety architect, these are the terms that are going to be used repeatedly, and you might have to, let's say, contribute or support in some of these processes. So once you have completed that analysis, you know what kind of safety mechanisms that you need to put in your design. So you have broadly two different categories of safety mechanisms. One is hardware safety mechanisms and one is software safety mechanisms. So some of the hardware safety mechanisms are pretty common. You might have heard about them. The CRC mechanism, PCC, BIST, which are memory based, logic based, voltage monitors, clock monitors, parity bits, end-to-end protection is a software part. Core self-test is a software based safety mechanism. Then you have something called a lockstep core. So most of these are hardware based, but a couple of them are software based safety mechanisms as well. So depending on what is the safety standard that you are complying to, a decision will be made by the architect along with the safety manager regarding what kind of safety mechanisms will be implemented in your design. And that will obviously have an effect on the verification effort. So I'll go over the aim of the safety verification quickly. So this is basically to make sure that the goals that you have derived at the start of the process are not violated. The second part is the failure modes and their propagating effects. You have to make sure that you are actually testing them vigorously in your tests. The third and the most important part, I think, here is the temporal behavior, which you can see on the left-hand side. Talk about this a little bit, where you have to make sure that whenever a fault occurs, the system is able to move to a safe state and it has enough time to recover, and depending on what kind of architecture is being designed, let's say inform the top level system or the subsequent outside world or whatever. If there is a processing capability in the same chip, then the same chip will be able to make that decision as well. But this temporal behavior needs to be verified. The second last part is the effectiveness of safety mechanisms. This is where terms like diagnostic coverage come into picture, and the different kinds of methods that are deployed. So there are broadly 3 different types of tests that we do as part of safety. This is the one of the very basic tests that we do, which is verification of the functionality of the safety mechanism. What I mean by that is, I inject a limited amount of faults, and I check whether those faults are getting detected by my safety mechanism, and I see an appropriate behavior at the output side. So the only purpose of this kind of a testing is to make sure that my safety mechanism implementation is okay or not. So this tells me whether the implementation of the safety mechanism is all right. So functionality wise, it is working fine. So this is one very simple test, but it is extensively used across different safety mechanisms. One of the focus areas of this particular test is the detection, propagation, and reaction. So this again, basically what this means is we have to make sure that the temporal behavior holds true. So whenever there is a fault injection, you have to detect it in time, make sure that it is propagated to an appropriate place, which is a central fault controller or a local fault controller, depending on your architecture. And you give either the chip gives out a proper response, or any central processing unit, which is part of the overall system, gives you an appropriate response. What that response might be depends on the architecture. It can be anything from an interrupt to a complete POR. So that fully depends on your safety architecture. This is one of the most important things of functional safety, which is making sure how effective your safety mechanism is. So in the first type of test, what we have made sure is our safety mechanism is working as implemented. What that tells me is, yeah, the implementation wise, it is fine. But let's say if I have I've injected 100 faults in a particular DOT, out of those 100 faults, how many of those faults can my safety mechanism safely handle? How many of those faults can be safely detected? How many of those faults are going to affect my output? So all these kinds of things are checked in a let's say a methodology where you kind of figure out what is the effectiveness of your safety mechanism. And this is where the fault injection simulations come into picture. Generally, this is done at IP level or subsystem level, very challenging to do at SOC level. Even at IP level, yeah, I mean, it's a problem because it takes a huge amount of time. One of the problems that we have here is this is not a short-term kind of a activity. Also, even if you, let's say, implement it, you need to make sure that you implemented it at the gate level, because the data that you are going to generate out of this will be accepted by the assessor or the auditor only if it is gate level data. And that is where the challenge comes, because all these things that we are kind of doing, right, the previous method, this method, all of this is towards a certain goal, which is to make sure that my design is compliant to the standard. And how do I demonstrate that? By showing that I have enough data, I have enough evidence for all the tests that I'm doing in terms of traceability, in terms of properly capturing all the, let's say, data, each and every data that is captured. I need to present the evidence at the safety assessment, which will happen towards the end. So this is a small kind of case study that we had done 3 years ago. Following the same methodology, we did this to check the effectiveness of core self-test library. So we wanted to, this was an ASIL B chip, and it was a single core chip where we had a core self-test library as part of the ARM Cortex M3 core. And what we wanted to do was we wanted to quantify the diagnostic coverage for that core self-test library. So it was an extensive exercise that we did. There's, I mean, I'll not go into the details, but those are the results that we had. Ultimately, I mean, what this exercise helps us to do is, right, so it tells me that, let's say in scenarios where I don't have the hardware budget for, let's say, using a lockstep core, I can use a core self-test library instead, and using as, let's say, an exercise which looks something similar, I can demonstrate to the safety assessment team that even though I have a combination of hardware and software safety mechanisms working in tandem, I have enough evidence to show that they will capture 90-97% of the faults, which is good enough for ASIL B. If anybody is interested, you can go and actually look at the paper. The third most important thing that we have as part of functional safety verification is nothing but the self-test. So when you have an SOC which is basically going to be in the outside world, you have to make sure, and it is going to be involved in making safety critical decisions, let's say during your driving experience, you have to make sure that the circuit is on the up and up every time you actually start your car. So that is where this periodic self-testing feature comes into picture. And you have to make sure that periodic self-tests are run so that the memories are in good shape, so that your logic, which is, let's say, digital logic or the control logic, which is not a part of the MBIS, that is in good shape. It also helps to, let's say, detect latent faults, because safety mechanisms are present to detect faults in your safety critical logic. But if there are faults in your safety mechanism itself, self-testing will actually help you to detect them. It makes sure that safety mechanisms themselves are robust and available. So there are different ways you deploy these self-tests. So one of them is pretty common, right? Offline and online. Online will be during boot, and offline will be application mode. There are challenges which come with this. It is not a silver bullet. There are, as we know, right, there are pros and cons for this as well. So I'll quickly go to them. So once we have these broad three methods of verification, we see that there are ways in which we can make our system as robust as possible. We can add all sorts of safety mechanisms. We can add, let's say, periodic self-testing features, but all of this will come at a cost. One is the verification effort will go up. The second is the amount of time, let's say, that is, let's say, when it comes to the products that I work on. This is one of the latest radar products out of NXP. So what this does is, you have to make sure that your chip is available for the maximum amount of time for its main mission. So whenever there is, whenever the chip is undergoing any kind of self-test, that duration is basically a kind of duration where it is not doing its main job. So you can have repeated self-testing during the radar cycle, but that itself means that the radar is not actually doing its main job during that time. So you can have periodic self-testing, but it comes at a cost of system availability. It also has its implications on basically the currents and voltages, because if you are going to put the entire chip or at least some part of the chip under self-test, you can assume that, yeah, the current consumption and the voltage will be pretty high. So you have to make sure that you are adhering to the current and voltage budgets. There are also temporal budgets. So we have certain time interval given for boot, let's say, and you have to make sure that your self-test will have a certain budget. So you cannot keep on going and testing out your chip. So you need to make sure that you are testing out critical parts of the chip during that particular time window. You cannot exceed that time window. You cannot, let's say, because you have an overall budget for boot, and within that you have a budget for your self-testing. One of the other challenges that we have here is during gate level simulations, it is a real pain to kind of test all these self-testing scenarios, because it is not just, let's say, running one particular partition, it is multiple partitions running in parallel. So the time, actually, the run times are also very, very critical here. So all these things actually make you, I mean, so on one hand, you have all kinds of safety mechanisms, but making sure that they work properly, making sure that they are adhering to, let's say, all the architectural specifications that you have, making sure that you are actually fulfilling the customer's criteria, that actually becomes a challenge. And this is the last part which I was talking about, preparation for the confirmation measures. So all the effort that we have taken till now right from the project definition phase till verification, till gate level simulations, all kinds of quantification scenarios that we have done. All that will come to nothing if you are not able to actually pass the safety assessment. So we have an independent safety assessment team which will come and do a safety assessment for your chip before tape out. And so that is basically to make sure that you are complying to ISO 26262, and you will have something called a safety audit, which is basically before the product goes to the customer, which is making sure that you are actually adhering to the overall process. So the assessment will actually look at what you have done while from the design to verification phase, but the audit will make sure that you have actually adhered to the process right from the project definition phase. So here our responsibility is, I mean, we are just a stakeholder in this process, right? So there will be safety architects, there will be design architects, all kinds of people will be involved in this assessment. But our job as verification engineers will be to provide robust data, robust evidences for all the scenarios that we have done. What I mean by that is we need to, first of all, make sure that all of our, let's say, verification data is captured in a centralized location. We have faced questions like, even going to the assessor has gone into details like how have you actually tested this scenario, where have you stored this diagram. So it cannot be a theoretical exercise where I just show them some PPT and we pass the assessment. So the assessor is actually going to take a huge amount of time to make sure that you have done what you are actually claiming that you are doing. So he will go into the requirements, he will go into the simulation databases if necessary, he'll go into change management data. We have had queries or findings coming back to us saying that even, let's say, we had followed a normal process, right? So during the project execution phase, there was a change in the requirement. So the normal process would be the architect or some senior guy raises a ticket for that requirement, then the verification people check that requirement, and that's about it. We add that test in our V plans and in our regressions. But that additional requirement which was captured as part of a ticket, but we had not gone back and updated our original safety requirements. So that kind of created a hole. So there has to be a traceability right from the top to the bottom in terms of what are my requirements, and they should be able to actually trace at each hierarchy level how you have addressed that. So, I mean, at least from speaking from a personal point of view, we need to put in adequate effort to kind of prepare ourselves for these confirmation measures as well, because we spend a lot of time in verification, but if we have to make sure that the effort that we are putting in for verification actually is going to count, then we have to, because it's like an examination for all of us, where he'll actually give you a detailed finding report and you have to address those findings. Otherwise, they will not actually give you the ASIL rating, which you need to sell your product. So these are some of the challenges. I think some of them we have already discussed. One of the problems that we always face is we have a limited amount of time for doing fault injection simulations, right? Most of our time will go into functional testing. We barely have enough time to basically test out all the scenarios in functional mode. So we need to actually figure out a way to do more and more fault injection testing, which is actually in line with the operational profile. So we generally, what we do is we do standalone testing of a particular IP or a block. We kind of test it, but what is going to be the implication at the system level, that perspective is generally missing. So we have to make sure that we have to mimic our fault injection scenarios in mission profiles, and it's not that easy because a lot of different things come into picture here. But that is one of the areas where we need to work on. Predicting effects of low-level faults at the system level. And the last one is, I mean, as I said, right, safety mechanisms will come at a cost. So you have to make sure that you have a balance of hardware safety mechanisms and software safety mechanisms. So technically or theoretically, at least, software safety mechanisms are easier to develop. I mean, the development time is less. I mean, some people might take problem with that statement, but is there a way we can kind of make sure that at least in some places having a higher level software safety mechanism be a substitute for, let's say, multiple hardware monitors that are present, And that software safety mechanism, we can actually demonstrate that, yeah, it is robust enough if we have enough data to back it up in terms of diagnostic coverage, in terms of all the failure modes that we have taken a look at. So that is something we need to think about. That's about it. Thank you. Any queries? Mm-hmm. Mm-hmm. Yeah. So how do you? Yeah, that is a challenge, right? So that is why, I mean, one of the issues that I wrote here is how to make sure that the fault injection scenarios that we run are as close to what the customer is going to be running at his level, at his end. So it is never going to be the case where the scenarios that you have tested are going to be enough. There will always be queries from the customer saying that, hey, we are trying out this scenario, which might be slightly adjacent to what you have tested. But yeah, I mean, the only way to do that is learn from your experiences and try to, I mean, one of the things that I've kind of learned is to make sure to interact more and more with the safety architects, with the IC architects, because they will know what kind of scenarios the customer is expecting. As verification engineers, we generally tend to kind of look at our requirements, and we are satisfied once our safety requirements or let's say verification requirements are satisfied. But we need to kind of keep a ongoing dialogue with the architect, with the IC architect, with the product architect, as to what the customer is expecting. If you have an already existing customer, then it's actually good to have a periodic interaction. They already have an interaction for software development, for all kinds of things. So that way we can actually try to gauge the use cases that they are trying to run. But yeah, it's always a cat and mouse game. We have to kind of keep learning from our experiences and try and figure out and what exactly can be done. I mean, one of the problems also is all these things ultimately, if you have to say confidently that we have checked, right, most of the things you need to check it at the gate level and at the SOC level. Then it becomes a problem, because the gate level simulation, you don't have much time actually. So you have to figure out how to balance all these things. In this scenario where you have a problem at the system level, hopefully, I mean, it is our design is flexible enough to take care of those issues. A lot of the times, actually, changing the sequences a little bit, configuring them in a different way, we can actually give them a workaround. But it all depends on the kind of scenario. Sometimes there is no option. If it's, for example, things like when you are running self-test for multiple partitions, right? If you are shooting, your current and voltages are shooting up. I mean, there's no other way. You can either decide that you are only going to run self-test for a limited amount of partitions, so that your current voltages don't shoot up, or you have to think about some other way. Hopefully, and I mean, the hope is, yeah, software configurability is there, so you can actually, based on your experiences and interaction with the customer, try and suggest them workaround. I think if you have done your verification to a good enough level, and your architectural, I mean, the architects are kind of involved, right, intimately with you, then I think you'll be able to take care of most of the problems. But yeah, in rare scenarios, it will need a yeah, that depends on what kind of tests that you are running. For the first type of test, I mean, it will be a regular thing, that the amount of testing that you will do is limited. For the quantification purpose, yeah, you will try to run the major use cases for your main use cases for your chip. So for a radar chip, there are, let's say, a limited set of use cases that I'll run, right? So I know what kind of things to expect in terms of sending data, receiving data. those kinds of scenarios I'll try to run and see if things are running okay even if I inject faults. Okay. Okay, thanks a lot for your time. Thanks for having me.